Good morning and welcome back. Today we're going to be talking about independent events. So we're going to first do a couple of examples using our intuition. After that, I'll give you an algebraic meaning of independence, and then to end this, we're going to use examples with the algebraic definition of independent events. So let's begin by talking about independent events from an intuitive standpoint. So intuitively, two events A and B are independent if the occurrence of A has no influence on the probability of occurrence of B. Now we're going to use our understanding of this sentence to do a couple of problems. So let's check the first example out. So here it says a bag of marbles contains 5 blue and 8 yellow. Find the probability of selecting a blue marble on the first draw and a yellow marble on the second draw if A, the first marble is replaced, and B, if the first marble is not replaced. I will use a couple of placeholders to help me out with this problem. The first placeholder being the first draw, or the probability of the first draw, and then I'm going to multiply this by the second placeholder, the second draw. That will give me the total probability of selecting a blue marble on the first draw and a yellow marble on the second draw if the marble is being replaced. So let's count these marbles because we need to get the sample space. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now I want my first draw to be the probability of obtaining something that is blue. And here I have 1, 2, 3, 4, 5 blue possibilities. So the probability here is going to be 5 out of 13. 5 blue out of the 13 on our sample space. Now, let's say that we're doing this, and suppose that I pick this marble, right? Because that's my probability. And here we have 13. But now what the problem is saying is that the marble is getting replaced. So let's pick our blue marble that we just picked, and let's put it back inside. And now let's do the second event. My second draw, we have to get a yellow. So now we have 1, 2, 3, 4, 5, 6, 7, 8 yellow out of a total of 13 on our sample space. So that's going to be 8 out of 13. And if we multiply this across, we get 5 times 8, which is 40. And then 13 times 13 is 169. And we have a approximation of 23.7%. Now let's do part B. This one's a bit more interesting, where the first marble is not getting replaced. So let's go ahead and set up our placeholders on this situation as well. Now on our first draw, we have to get the probability of something being blue. And again, we have 5 choices out of 13. So the probability for our first draw should remain the same, 5 out of 13. For my first draw, I got a blue marble, and now I want to see what happens on my second draw. However, for this problem, the marble is not replaced, so this marble right here, I'm not going to do anything with it. I'm going to keep it there. So let's just say that we throw it away in the trash. We're not replacing the marble. So now here it says, what is the probability that the second marble is yellow? So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8 of them. So our probability is 8. But now you're going to see that the sample space changed, because now we don't have 13 total marbles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the probability changes to 8 over 12. And if we multiply across, 5 times 8 is 40. And then 13 times 12, 9, 10, 11, 12, 13 is going to be 156. which approximates to 25.6%. So 40 over 156, 25.6%. And that's how you do these replacement or not replacement marble problems. And here, this is the intuitive way of doing these independent event problems. But before we get more rigorous, let's just use this idea because it's very, very useful to use this notion of placeholders. So let's do one more example and then I'll have you try some on your own. And here, let's begin by doing 3 review problems from a previous lesson. So here we have a large bag and it has 6 pink marbles, 4 blue, and 3 red. And we have to find the probability of getting a red marble on our first draw. So we have to calculate the sample space first by counting all of the marbles. So we have 6 plus 4 plus 3, and that's going to give us a total of 13. So that's the sample space. And out of these 13, 3 of them are red. So we have a 3 out of 13 chance probability of getting something that's red. And that approximates to 23.1%. And now let's find the probability of pink or blue. So here we want everything that's pink, so that's 6, plus everything that is blue, which is 4. And then we're going to divide that by the sample space of 13. So 6 plus 4, that's 10 over 13. You could also, that's 10 over 13. And here that approximates to 76.9%. And part C, what is the probability of pulling a non-pink marble? So let's get rid of everything that's pink, and we're left with blue and red. So we have a 4 blue plus a 3 red. So 4 plus 3, that's the amount that is not pink. We're going to divide that by the sample space of 13, and that gives us a 7 out of 13 chance of pulling a non-pink marble, and this approximates to 53.8%. And now let's attempt problems with independence or non-dependent events. So here we have the same thing, 6 pink, 4 blue, and 3 red. And now it says, what is the probability of pulling a pink marble, replacing it, and then pulling a blue marble? I got my placeholders, and I also underlined the important part, replacing the marble. So for my first draw, what is the probability of getting something that's pink? So that's going to be 6 out of the sample space of 13. And now replacing the marble, the one that we got here, is not going to make any changes to the sample space. So we still have the sample space of 13, and now we have to focus on the probability of blue. So how many ways can we achieve blue here? And that's a 4. So we have a 4 out of 13 chance of getting blue. And now we can multiply these across to get the total probability. So 6 times 4, that's 24. And 13 times 13 is 169. This approximates to 14.2%. Okay, and now let's focus on this one. I underlined the important information, and I have my placeholder set, and I also drew the marble so you can see what's happening visually. So for my first draw, I want the probability of getting something red. So here we see that we have a 3 out of 13 chance. 3 possible ways of getting red out of the 13 total marbles. But now here, the key part is that we don't replace the marble. So here we're under the assumption that we got something that's red. So I'm going to pick this red marble right here, and I'm going to move it. I'm going to move it out of the way. So right here. And now, since I'm not replacing it, I'm just going to throw it in the trash. So let's erase this. It's no longer there. And now we want to get the probability for our second draw. We want the probability of getting something red again. but you can see that two things happened. The sample space changed, and the number of red possibilities also changed. So here we have a sample space of 12 now. We have a total of 12 marbles remaining, and now we have two possible ways of getting red. So now we have a 2 out of 12 chance. And here 3 times 2 is 6, and then 13 times 12, that is 156. And let's put that in the calculator, and we get that this comes to a 3.8% approximation. So here, when we replace the marble, you can see that this probability was not affected by this one. So these events are independent from one another. On the other hand, when you don't replace the marble, this depends on the probability of this part. So these are not independent. Okay, so try out some problems, and then we'll come back and we'll use a nice formula for independence.